Good evening, everybody. Legacy of the Hubble Space Telescope. As you can see from the subtitle, I'm talking about how it changed from a white elephant to a white knight. Excuse me. So there can be very few people who don't recognise the iconic Hubble Space Telescope. Not just astronomers, not just scientists, but I think if you stop a man in the street and show them that, they will know what it is you're talking about. In this talk, I'm going to be covering a little bit of the background, the need for a space telescope and what are the alternatives for ground-based telescopes, a little bit of the history, how the mirror was flawed in its manufacture and how the optics were subsequently fixed, and then a little bit about the legacy, what it's done for us in terms of our understanding of the universe, and a little bit about how it's touched the public consciousness and brought along the public for the ride, as it were. And then I'll finish with a future look covering the same ground as I started with, the need for future space telescopes and ground-based alternatives. This is a very useful summary. It's a little bit busy, so don't worry about all the detail. This gives us an idea of the number of telescopes that are around and their relative size. So these are all to scale. If you need it, the bottom left shows you a tennis court and the bottom right shows you a basketball court. And if we look in the top left, that's the largest telescope with an objective lens, the Yerkes Observatory 40-inch refractor. And you can see the telescopes since the turn of last century have been getting larger and larger. The space telescopes that I'm going to be talking about are in this bottom left-hand corner. So there you can see the James Webb Space Telescope, the Hubble Space Telescope, which is of course what we're talking about mostly this evening, and also a couple of other space telescopes, Gaia and Kepler, and I'll mention those a little bit at the end of the talk. But you can see that to scale, these mirrors are very much smaller than not only the largest telescope on the ground at the moment, this one up here in yellow, the Gran Telescopio Canarias on the Canary Islands, perhaps that's appropriate that it's yellow then. That's the largest ground-based telescope at the moment, but you can see that these monsters are coming along before too long. The 30-metre telescope in Hawaii, the 40-metre European extremely large telescope coming along in hopefully only a few years' time. So if we have these large or huge telescopes on the ground, then why are we considering putting up more space telescopes? Why was the Hubble Space Telescope built in the first place? And why are we thinking of future space telescopes? Well, we know that telescopes have come a long way in the 400 years since Galileo. On the left there is the Yerkes telescope, on the right the 5-metre Hale telescope. Refractors got larger and larger up to a maximum size of about a metre or so in diameter. And then reflecting telescopes using mirrors started to take over. But there's always been this drive to go from smaller objectives, whether they be a lens or the mirrors of reflecting telescopes, there's always this drive to go to larger and larger telescopes. And that's been driven for two reasons. Larger objectives or larger mirrors will collect more light, so that means you can see fainter objects, but also larger mirrors will have a higher resolution. They can see more detail. So they can either see smaller objects at a given distance, or they can see similar objects to an even greater distance. So there's always advantages for going to larger and larger mirrors. So if that's the case, why would we consider putting a relatively small telescope in orbit when we've got all of these large telescopes on the ground? And the advantage, of course, is that we can get above the Earth's atmosphere if we go into orbit. The Earth's atmosphere doesn't absorb much of the starlight in the visible part of the spectrum. Most of the light reaches the ground, clouds notwithstanding. But the Earth's atmosphere is turbulent, it's chaotic, and therefore the starlight, although most of it will reach the telescope, the starlight will be blurred, and therefore we won't see the detail in the stars or the distant galaxies that we're trying to image or obtain spectra from. So we want to get rid of the turbulent effect of the Earth's atmosphere, and the best way to do that is to get above the atmosphere. We would, of course, still like to have the largest telescope possible in orbit, but there were practical considerations. The size of the Hubble Space Telescope mirror is about 2.4 meters in diameter, and that's limited not by the cost or the practicalities of making a bigger telescope, but simply that is the largest object that could fit inside the cargo bay of the shuttle, which was the only object at the time that could launch such a space telescope. So by getting above the atmosphere, we get away from the blurring effect of the atmosphere. And if you think about the resolution of a particular sized mirror, we can calculate that based on the laws of physics. And we know the effect of the atmosphere by looking at the so-called seeing, the effect of the turbulent atmosphere on the tops of mountains, for instance. We can calculate that by putting the Hubble Space Telescope in orbit, the resolution is something like 10 times better than a similar sized telescope sitting somewhere on the ground. So a factor of 10 in resolution in detail is certainly worth having. Let's think about the history. When does the story of the Hubble Space Telescope start? Perhaps a little earlier than you thought. 1970 is when NASA started planning for a large space telescope. So people were still jumping around on the moon. The Apollo program hadn't finished by the time NASA started looking beyond Apollo to what's the next big project that we're talking about. And 1970 was the first big milestone. That's when they started the planning. Would anybody care to guess what the second big milestone was? Yep, that's right, it was cancelled. Congress withdrew all funding, saying, great idea guys, wonderful idea, but way too expensive. We can't afford this idea of putting a telescope into orbit. There was then a lot of crosstalk between scientists and politicians and the funding bodies, and eventually it was agreed that by collaborating with ESA, the European Space Agency, NASA wouldn't have to bear the whole brunt and then put the burden on the American taxpayers when they could pull in money from European taxpayers as well. So in 1978, Congress agreed to fund the Large Space Telescope in collaboration with ESA. There is still a tendency to think of the Hubble Space Telescope as a NASA telescope, but we have to remember that it's always a NASA-ESA project. So it was put out to tender, and the spacecraft construction was tendered to Lockheed and the optical telescope assembly to Perkin-Elmer. So one thing we have to bear in mind is, as astronomers, we tend to think of the Hubble Space Telescope simply as a telescope. But strictly speaking, it's not. It's really a spacecraft with a telescope inside it. And that's the way NASA and ESA approach this particular project. You get a company that's well versed in building spacecraft to build the systems, and then inside that you put the optics of the space telescope, and then you have some instrument manufacturers making the cameras and the spectrometers. So spacecraft Lockheed, effectively the telescope part of the spacecraft, went to Perkin-Elmer. Perkin-Elmer being experienced in manufacturing optics. So very shortly after the tenders were agreed, in 1979 construction of the primary mirror began, and Perkin-Elmer produced the 2.4 meter diameter mirror. It only took about 2 years from construction starting to the final polishing and testing, and everybody saying, yep, the mirror is now perfect. It is now absolutely within specification of what was required for a diffraction limited optics of this particular diameter. 2 years might sound quite quick, but bear in mind it is by no means a large telescope in comparison with ground-based telescopes, which might have mirrors up to 8 meters in diameter. This is only 1/3 of that diameter, so it's only 10% of the area, and therefore the manufacture of such a mirror, even to very high precision, didn't actually take that long. So 2 years after starting, they declared that they had a complete and essentially perfect mirror. Congress were aware of the fact that the primary mirror would be critical for the telescope. Who wants a telescope where the primary mirror doesn't work properly? So it was agreed right from the get-go that there would be a backup mirror. So whilst Perkin and Elmer were working on the primary mirror, a backup mirror charged to Kodak was made in parallel. So this was made in parallel such that if Perkin-Elmer hit any problems and declared that they couldn't make the mirror, there would be a backup and we wouldn't have to trash the entire project. Congress effectively insisted that that was the case to make sure their investment of money didn't go to waste. So Perkin-Elmer said, our mirror is fantastic. So in 1981, it was agreed, well, actually, we don't need the backup mirror because the primary has been made, it's manufactured, tested, and it's fantastic. So it was agreed at that point that any work on the Kodak mirror, it was effectively finished, but any further work on the Kodak mirror was stopped, and the Kodak mirror was then put into a museum. 1983 was the original planned launch date, and at that point the Large Space Telescope was officially named the Hubble Space Telescope, of course in honour of Edwin Hubble, who earlier that century had done a lot of pioneering work on the Hooker telescope and on the Hale telescope, looking at the recession of distant galaxies, what eventually became known as the Hubble law, where the recession velocity of a galaxy is proportional to its distance, and that ratio became known as the Hubble constant. There were a few setbacks in the middle of the 1980s. The launch date was put back due to a few schedule slips on the part of Perkin-Elmer and on the part of Lockheed. By 1986, the budget had escalated. I can't remember what the original estimate was, but by 1986, the budget had reached over $1 billion and was still rising. Unfortunately, come 1986, even though it was a few years behind schedule, there were more delays to come. 1986, unfortunately, was the year of the Challenger disaster. The shuttle exploded on launch, and therefore the entire shuttle fleet was grounded. And even when the shuttles were flying again, there was a large backlog of the number of satellites that were destined to go into orbit. The military were at the head of that list, and so the Hubble Space Telescope had to wait a little while until it got its launch window, and eventually it was launched in 1990. So we can think of the Hubble Space Telescope as being 30 years old in terms of its launch, but clearly in terms of its construction and in terms of its planning, then it's 10 or 20 years older even than that. When it was launched in 1990, the total construction cost was estimated at about $2.5 billion. That doesn't include the cost of any future shuttle service missions to replace instruments in the course of time. So a very expensive project indeed. One point about the design before we move on. The Hubble Space Telescope is a Ritchie-Chrétien design. Some of you might be familiar with those words, but basically it means that the primary mirror is not a sphere, not a parabola, it's a hyperbola, a conic section which is slightly different from a parabola. A lot of telescopes in the last 50 or 60 or 70 years have been built with hyperbolic shaped mirrors. The last really big telescope to have a parabolic mirror is the Hale telescope on Palomar Mountain with its 5 metre or 200-inch mirror. So perhaps you can remember from school focusing with a little light box. A parabolic mirror is the shape that will focus light from infinity to a point. But unfortunately, parabolic mirrors have a particular aberration in that if you look at light that's hitting the mirror at an angle, you have a particular aberration called coma or chromatic aberration. And hyperbolic mirrors are slightly different from parabolic mirrors in shape. I'm not going to go into the details or the maths of how they differ, but they're a slightly different shape, and that gets rid of this particular aberration. But it does mean that the mirror itself doesn't focus light from infinity. You need 2 parabolic mirrors in order to get the telescope to work correctly, and that's relevant for what's about to come. When the telescope was in orbit, the horror slowly dawned on everybody in ground control looking at the images coming back from the telescope. They realised that it would not focus. They were expecting to get nice pin-sharp images. Here on the left we can see a star field where the stars are nicely point-like, but what was actually observed is something like the horrible mess on the right. Most of the light from this bright star does appear to be focused into mostly in this middle region. Perhaps 80 to 90% of the light is focused in the middle, but a large fraction of the light appears to be in this horrible halo, which is going to completely destroy the ability of the telescope to see and resolve fine detail. A lot of to and froing was done and tried to move the secondary mirror relative to the primary to see if the focus could be improved. But eventually it was admitted that the mirror, the primary mirror, had a particular aberration called spherical aberration. It had been made incorrectly and had an aberration that should not be present. Let's just make sure we understand what spherical aberration means. Let's forget about hyperbolic mirrors. Let's just imagine that this telescope is supposed to be focusing, using this mirror, light from infinity, and if we draw a few light rays, we can see light hits the mirror and comes to a focus. Fine. But what about light that hits a different part of the mirror? That should be focused at exactly the same point. But with spherical aberration, the focal length is a function of where the mirror is hit by the light. The focal length should be irrelevant as to, the focal length shouldn't care where the light hits the mirror. All the light should come to a focus regardless of where the light hits the mirror. But in spherical aberration, the focus, the focal length, if you like, changes depending on where the light hits. And it gets worse the further away from the center line you go. So any light hitting the edge of the mirror comes to a dramatically different focus than the light hitting the center of the mirror. So we're not saying here that the Hubble Space Telescope mirror has been made in the shape of a sphere, but spherical aberration is a way of describing the aberration in which the focus of the mirror is a function of where you hit it, which should not occur except in spherical mirrors or in any mirrors which have been made slightly the wrong shape, in which case you get this result. So if we imagine where should we put our CCD camera or our spectroscope slits in order to image, well, the region that seems to have the smallest, if you like, circle of confusion is around here. So we could put our detector there, but of course some of the light will be focused behind it, some of the light in front of it. If we move the CCD camera or spectroscope slit to that particular position, then most of the light is focused very nicely to a point, but it's also clear that any light that's focused and comes to a focus in front of the CCD will then produce this horrible halo that we see in the observed star pattern here on the right. So that's essentially how it was diagnosed, because that particular halo is characteristic of this particular aberration that we call spherical aberration. So remember, what was expected were nice point-like star images. No star image will ever be, strictly speaking, a point, but it will be almost a point within a pixel or two of the chip being used to make the image. It's still better than what you would expect for a telescope of this size if it was sitting on the ground. To give you a rough idea, if you take a 2.4 meter mirror that is essentially perfect, put it on the ground, what would you expect on the scale that we're looking at here? Then that, roughly speaking, is what you would expect. We're not getting pinpoints because we're getting the blurring of the Earth's atmosphere. So we're doing better than a telescope of the same size sitting on Earth. Well, yeah, great, but we've just spent $2.5 billion putting it into orbit, and we expect to get far better than that middle panel. We want something more akin to that bottom panel where the stars are nicely crisp and in focus. So how can you spend billions of dollars on a project like this and get it so wrong? How could a mistake like this be made? Tests carried out during the construction indicated that it was the most precisely figured mirror that had ever been made. It was estimated that the surface roughness, the mountains and valleys, the bumps and the grooves in the surface in the figure of the mirror were no bigger than about 10 nanometers, 10 billionths of a meter, or 10 millionths of a millimeter if you prefer. And to give that some sense of scale, that's equivalent to, if an object was the size of the Earth, if you scale up the Hubble mirror until it was the size of the Earth, then these bumps, these mountains and valleys, would be about 3 centimeters or so in size. So yes, this is an exceptionally smooth mirror shape. But unfortunately, it was not the correct shape. It was extremely precisely figured to the wrong shape. It was off by a couple of microns or so. If you look at where it should be in the center of the image compared to where it should be towards the center of the mirror compared to where it should be towards the edges of the mirror, the difference was about a couple of microns. Now, 2/1,000,000th of a meter might sound very small, but remember the wavelength of visible light is about half a micron, so being wrong by 2 microns means that you're wrong by about 4 wavelengths of light. What you really want to be is to be accurate to a very, very small fraction of a wavelength of light to make sure all the light is arriving at focus and none of the light is interfering and cancelling out, which is what you would get if parts of the mirror are sending light to the focus with a different position compared to other parts of the mirror. So it was wrong by a huge 2 microns, 4 wavelengths of light. Well, the mirror, as I said earlier, is hyperbolic. If it was a parabola, all you'd need to do is to test it by focusing a distant object like starlight and check that you actually get a perfect focus. But with a hyperbolic mirror, you can't do that. The telescope is designed to work with 2 hyperbolic mirrors, and you can't make 2 hyperbolic mirrors and test them at the same time against each other because that's just totally impractical. You have to find a way of making one mirror and testing it and making the second mirror and testing it. And you can do that by trying to fool the optics, or the test rig if you like, into thinking that instead of being a hyperbolic mirror, let's pretend it's a spherical or parabolic mirror. You can add additional lenses to make the mirror look like a different shape to make it easier to test. And that's what a so-called null corrector is supposed to do. It's a series of optics that allows you to do the test to check the shape of your mirror. But unfortunately, one of the lenses in the null corrector was misplaced in the test rig that Perkin-Elmer used to test that they were grinding the mirror and polishing the mirror to the correct shape. It's thought that a washer was placed on a bolt where it shouldn't have been, and hence one of the elements of the test rig was misplaced by nominally about 1 millimeter or so. Well, yeah. It's easy to say with retrospect, but at the time it was not realised that that mistake had been made. There are other tests that could have been done, and it was said at the time, why don't we do a really cheap and cheerful test just to make sure everything's okay? A simpler test would have revealed the fault, but it was deemed unnecessary because this wonderful, very complex test that had been carried out said that the mirror was fine, the mirror was okie dokie. So a simpler test was deemed unnecessary, even though it would have cost a few $1,000s or maybe $10,000, a tiny fraction of the cost of the telescope. It was deemed unnecessary. And of course, the Perkin-Elmer mirror is sitting there in the telescope, and what is thought to be a perfectly good backup mirror is sitting on the ground. It was made by Kodak, it was ground by Kodak, it was polished by Kodak, it was tested by Kodak, completely independently of the Perkin-Elmer test rig, and therefore there's no reason to think that it suffered from the same problem. So there's probably a perfectly good mirror sitting in the museum. But our problem is with a telescope in orbit. So what do you do about that? Well, the one thing that saved the Hubble Space Telescope from a complete scientific and public relations disaster was the fact that it was designed from the outset to be serviceable by the space shuttle, by shuttle astronauts. And that meant that there was a way out. In principle, you could say, well, let's just send the shuttle back up again, capture the Hubble Space Telescope, bring it back down to Earth, swap out the mirrors, well, double check the Kodak mirror first, put it in, send it back up again. But there was an alternative when they realised that there's a relatively cheap way of fixing the problem. There was already a spare camera sitting on the ground. This is not unusual when you send instruments into space. It's not unusual to have a non-flight version of the same thing. In this case, it's the main camera that's sitting on the ground, which is essentially a duplicate of the one that's currently in the Hubble Space Telescope. That meant they could look at the Perkin-Elmer test rig, they could go back to the test rig, try and figure out what was wrong. They realised what was wrong, and from that point on they knew precisely how the test rig was in error, and so they knew precisely what the figure of the mirror was. So the fact that it was wrong is not as important as the fact that they knew precisely how it was wrong. So they knew precisely how it needed correcting. So if this is a spare camera on the ground, the light from the main mirror would come in on this little mirror and then shine into the camera, which is part of this assembly here. If they simply added correctional optics to the camera, to the camera that's sitting on the ground, if they added correction optics knowing exactly what the aberration of the mirror is, they could correct it such that this camera would then produce perfect images. Well, that's fine for one camera, but the Hubble Space Telescope is not simply a telescope with a camera bolted onto the back. The Hubble Space Telescope has quite an array of instrumentation, as we will see shortly. A number of cameras and a number of different spectrometers. So you have to find a way of getting the light from the telescope, which we know has an aberration, to the other instruments. So this one is fine because we can fix that by putting in corrective optics. But what about the other instruments? Well, it was decided that a Swiss Army knife of corrective optics called COSTAR would be inserted in one of the instrument bays. One of the instruments would have to be sacrificed, and in its place would be inserted this Swiss Army knife of optics. This is the actual COSTAR itself after it came back down, which I'll explain a little later. But to make it a little easier to see what's going on, here's a little model of it. So you can see that there are a number of these little discs, these little mirrors, sitting on the end of these coloured arms, and what would happen is that when a particular instrument was being used, one of these arms would flip out to place one of these mirrors into the light path between the telescope and the instrument that the light was being sent to. And these little mirrors are not flat, they are made precisely the shape necessary to correct for the aberration in the main mirror. So if COSTAR is made correctly and if it's installed correctly, then it will be able to send, if you like, corrected light, light in which the aberration has been corrected for, into the other instruments in the back end of the Hubble Space Telescope. So the scientists and the engineers and the astronauts that fitted it were told, let's get this right, guys. At the moment, we've got a white elephant and it doesn't work properly. Hopefully, when we fit COSTAR, we will then end up with all the instruments working correctly. If we don't get this right, then Hubble will remain a white elephant. And that won't simply be the end of the Hubble Space Telescope program. It will probably be the end of NASA. No pressure, guys. But Congress will not give money to NASA ever again if, after spending billions of dollars, they make this sort of a mess. So this has got to work. So, as I said just a moment ago, remember that it's not just a single camera. At any given time, the Hubble Space Telescope has got probably at least 2 cameras and 2 spectrometers operating at any given time, which can be swapped backwards and forwards depending on where the light is sent. The light from the telescope can be sent to this camera or that spectrometer, or this camera or that spectrometer. And these cameras and spectrometers have actually been swapped out, as I'll show you in just a minute, over the various service missions. So what's going on behind the main optics of the telescope? The cameras, they might be labelled wide-angle cameras or high-resolution cameras. They're physically not necessarily different cameras, they're just referring to what is the effective focal length with which they're being used. And just for reference, the nominal focal length of the Hubble Space Telescope is a whopping 58 meters. For any of you with telescopes with a focal length of 1.5 or 2 meters, 58 meters is a stunningly large focal length. Let's just make that picture on the left a little bit bigger so we can see what's going on. Notice that if we think of this again as a spacecraft, we have the Hubble Space Telescope being a certain length, but the optics only occupy this region in the middle. Perhaps less than half of the whole length is the optics. There's the primary mirror and there's the secondary mirror. Most of this front end is effectively just a sun hood to try and stop stray light entering the telescope, and there are instruments around the primary mirror and behind the primary mirror. A number of different instruments which I'm not going to go into in any sort of detail. But it is interesting, I think, to look at the service missions that were carried out for the 20 years or so after the Hubble was first launched. So again, I'm not going to go into details, but one of the first things that happened was that a service mission went up to replace camera 1, which is the standard camera that it launched with camera 2, and camera 2 is the one that was on the ground that has had the corrective optics fitted, so now that camera should produce wonderfully clear images. And this particular instrument here, it doesn't matter what it is, that is the instrument that was sacrificed. That was effectively thrown away, it was taken out of the Hubble, brought back to Earth, and that instrument was replaced with CoStar, which then feeds the corrected light to all of the other instruments in the Hubble. Whilst they were there on that particular service mission, the asterisk simply means whilst they were there, they did a quick tune-up. They tweaked the gyros. The gyros are responsible for pointing the Hubble Space Telescope precisely in a given direction, and the electrical systems needed a little bit of a tune-up as well. These instruments down here, I'm not going to talk about what they are, but just to give you an idea, if the acronym ends in an S, it's probably a spectrometer. And if the acronym ends in a C, it's probably a camera. That's all you really need to know. So we've got one working camera, and CoStar is now going to make sure that this spectrometer and that camera are now working correctly. So that's what the first shuttle mission carried out. And as I'm sure you're all aware, the camera 2 took images, and yes, the problem was fixed. A huge sigh of relief on the part of NASA, because they realised that hopefully we are not going to fold. Although it's been a little bit of a disaster, we have managed to rescue it. A bit like Apollo 13, looked like it could have been a disaster, but they managed to get the astronauts home. It was a similar sigh of relief when it was realised that the optical problems had been cured. The next service mission was relatively minor. It didn't do anything with the camera or CoStar, but they replaced this spectrometer with another one, and they replaced this spectrometer with another one. Again, I'm not going to go into the details. Why would they swap out a spectrometer so early? Well, remember, it's not very early. It's 1997, 7 years since it was launched, but remember, it was built in the 1980s. And therefore already technology has moved on. So what was state of the art in the 1980s is no longer state of the art in the 1990s, and that's one of the advantages of the Hubble Space Telescope. It was designed to have its instrumentation swapped out. As things improved, then basically you can install the latest versions as you go through your service missions. A little bit later, service mission 3, they again tweaked the gyros. But then they had a little bit of a problem. Soon after that service mission, the grey area here for this spectrometer indicates that this spectrometer started to fail and wasn't giving good scientific data. So they needed to have another mission to fix that, and in the early 2000s, around 2002, they tweaked some of the electrical systems, and they fixed that particular spectrometer and got it working again. And in the final little slot here, you see one camera has been replaced with another. Yes, I know that's got an S on the end, so it looks like a spectrometer, but they pulled a fast one here, and they called this advanced camera for surveys, so it is actually a camera, not a spectrometer. So at this point, they have now replaced every instrument with a new instrument which has been designed from the outset to have the corrective optics built in, so there's no longer a need for CoStar, the Swiss Army knife that would otherwise send the corrected light to each of the instruments. But after that fourth shuttle mission, things started to go a little bit wrong. Some of the electrical systems started to play up, one of the spectrometers started to play up, and this final camera at the bottom there started to have problems as well. It was thought that maybe the fifth shuttle service mission would be cancelled because it was going to be quite expensive, and Congress were putting pressure on NASA to actually cut the bills, if you like. And obviously every shuttle launched to service the Hubble Space Telescope was quite expensive. But there was a large argument again between the scientists and the politicians and the funding bodies, which said we really need to get everything working as best we can, and we do absolutely need one more service mission. So in 2009 they had the final service mission. Technology has moved on, so it was possible to put in camera number 3 with a higher resolution chip to take higher resolution images. CoStar was no longer necessary, so you can bring the Swiss Army knife back down to Earth and put it in a museum. That's what we saw earlier, and that slot that was freed up at that point was then used by yet another spectrometer. The gyros were tweaked to make sure they were all working fine, the electrical systems were given a tune-up, the spectrometer was fixed, and these other two were given a tune-up as well. So when the final service mission finished in 2009, there were 2 cameras and 3 spectrometers, all in good working order, which means that the Hubble Space Telescope was firing on all cylinders. And as far as I'm aware, they've had no major problems since. So there's been a lovely area where we've got white and no grey for the next 10 years. It's been amazingly reliable for many years since. So how has the Hubble Space Telescope contributed to our understanding of the structure of the universe, the evolution of the universe? In other words, what is the legacy? It's not over yet in that it's 30 years old since it was launched, but there's no signs of it going belly up just yet, so let's hope it's got a few more years. But even if it finished now, what legacy would it give us in terms of our understanding of the universe? The examples are just far too many. It's done so much over the last 3 decades. I just pick out a few particular points. Cepheid distances, exoplanets, stars, galaxies, and supernova. So let's see what I can cover in just a few minutes. One of the things that the Hubble Space Telescope did was look out into this galaxy. It might look like a part of the Milky Way, but in fact this is part of Andromeda. Remember, the Hubble Space Telescope, with a focal length of 58 meters, only sees a very small patch of sky, so it can't get the whole of the Andromeda galaxy in its field of view. But it has sufficient detail, sufficient resolution to see a lot of the stars within the Andromeda galaxy. Some of these brighter stars are foreground stars in our galaxy, but a lot of the fainter ones are in the Andromeda galaxy. And some of these fainter stars are so-called Cepheid variable stars. They vary their luminosity with a time period that depends on how luminous they are. That's a well-known relationship that we can tell by looking at stars within our own galaxy. So if we can look at stars in the Andromeda galaxy and look at how they vary in time, we know what their luminosity is because of that relationship that exists for this particular type of stars. And if we know how luminous they are and we know how faint they look in the images that we take, we can judge the distance. And that enabled us to get the distance to Andromeda more accurately than any other previous telescope. And if we've got the distance to Andromeda, that's the first step of the cosmic distance ladder out to other galaxies, and hence we can get a much better idea of how large or how distant the various galaxies are. By getting that distance right, it gives us the first step to looking at more distant galaxies. And by measuring their redshifts, by using that to work out their recessional velocity, we then get the recession velocity divided by their distance, which we now know more accurately. That means that we know the Hubble constant more accurately. And one of the jobs, if you like, of the Hubble Space Telescope was to determine the Hubble constant as accurately as possible. And previously it was only known to an accuracy of about 10%. Now it's known to an accuracy more like 1%. So the accuracy with which the size of the universe and the expansion of the universe is now determined has been improved by something like a factor of 10. We're perhaps used to thinking of exoplanets most recently because we now know of thousands of exoplanets. Perhaps we forget how difficult it was to see exoplanets in the early days. So in the late 1990s and the early 2000s, the Hubble Space Telescope had the resolution to actually image individual planets going around a star. Here, a star is so bright, the actual star itself has had to be blanked out, and we get a lot of light scattering, which gives us this very odd effect that we're seeing here. But if we look in detail as to what's going on inside this cloud, we find that we have a condensation of a planet which appears to move over a period of a couple of years. So this is direct imaging of a planet moving around this star. In most other cases, when we're looking for exoplanets, we're using different techniques. We're using the fact that the light from a star might dim when a planet moves in front of it, or we're using the fact that the star might seem to wobble as a distant exoplanet goes round that distant star. But Hubble is one of the few telescopes that can actually image an exoplanet, and did so about, nearly 20 years ago now. Not only that, not only can it image, but because of the spectrometers on board, a reminder that imaging is very powerful, but being able to obtain a spectrum is arguably even more powerful. An image tells you what something looks like, a spectrum tells you what it's made of, or something about the dynamics. And in this particular case, the Hubble was looking at the spectra of the light passing through the atmosphere of various exoplanets, and using that we can determine something about the chemistry of these exoplanets and whether or not they contain any water in their atmospheres. Very important, of course, if we're trying to determine whether or not any exoplanets can harbour life. Hubble has imaged I don't know how many thousands of galaxies, and it's increased our understanding of galaxy formation, how they formed in the first place, how they grow, various odd structures, not just elliptical galaxies, not just spiral arms, but some very odd structures like this ring structure, which appears to be a sort of a spiral arm that has no beginning and no end. But one of the most profound results from the Hubble telescope, I think, is looking at great distances when we're looking for either supernova, which are very useful standard candles to give us an idea of these very large distances when we're talking about billions of light years. But also we get this effect whereby we see that when we have a large mass of, for instance, a large supercluster of galaxies, that large mass can distort space and can distort the way light reaches us. So just to show you what we're looking at in this image, let me show you what we're looking at if you like, us down here at the Earth with the Hubble Space Telescope. We're imaging a very distant galaxy here on the upper right, but in between the galaxy and the Hubble Space Telescope is a large cluster of these sort of slightly yellowish or orangey galaxies, and these are massive enough that they're distorting space around them. According to Einstein's theory of general relativity, mass distorts space, and because space is distorted, the light from the distant galaxy ends up being bent into various paths. Some of the light travels in almost a straight line to the telescope, but some of the light gets distorted by this very large mass. It's behaving like a very large irregular lens, and light passes through different parts of the lens and still ends up at the telescope. The shortest route will get to the telescope first, and some of the light you can see here ends up looking a little bit like a dog leg, and so that travel must be a greater distance, so it must take a longer time. So if a particular event occurs in this particular galaxy, it'll be seen first by the light that takes the shortest route, and then it'll be seen later by the light that takes the slightly longer route. And what's interesting is what we see if we blow up this region here. Let's go back to the original image. This galaxy here appears to have 4 bright dots in it. We seem to have 4 supernovae going off at once. Now, in any given galaxy, we would expect a supernova to go off maybe once every 100 years or so. What are the chances that 4 supernovae have gone off at the same time? Infinitesimal. So what's thought to be going on here is it's imaging the same supernova 4 times. And by taking the spectrum of these 4 dots, we can see that that is indeed the case. So what's happening is the light from this distant galaxy is being lensed, it's being distorted by an orangey galaxy that's actually sitting in the foreground, and that's giving us 4 possible paths for this supernova. So not only that, but remember that if we're seeing that supernova from the light that is taking the shortest path to us, what's going to happen to the light that's taking a slightly longer route? Well, any theorist that looks at this mass can try and calculate what the mass is doing and how it's affecting the light from these distant galaxies. This galaxy is not only visible here, but a distorted version of it is visible just upper left. And there's another version of the galaxy which is up here. These are all the same galaxy. It's being imaged multiple times, just like that supernova is being imaged multiple times because of the way the light is passing through this supercluster of galaxies. Other galaxies are indeed in the background, and they look quite distorted as well. You can see these lines in the distance, these little arcs, which again are more distant galaxies that are being distorted by the passage of light through the cluster. But in this particular case, this is an amazing find by Hubble, because they could see this supernova. The theorists could then tell them that this image that we're seeing in the upper right, that should be quite a few months behind, because it's taken a slightly longer path. The light from that galaxy is about 6 months behind the light from this particular version of the galaxy. So if here we see a supernova going off, what we should see is, if we look in this galaxy in 3, 4, 5 months' time, we should see the start of a supernova going off. Normally, we only catch a supernova after it's bright enough to see. But here, we've got advance warning of a supernova, because the light hasn't reached us yet from that particular route. And so the Hubble was instructed to go back and look at that galaxy in more detail 5 months later. And lo and behold, when it went back to that galaxy, it saw the supernova going off. This is an amazing collaboration of experimental results and imaging, and the theorists who can calculate how much space is distorted by the presence of a supercluster of galaxies, and hence we can then use it to actually augment our ability to make measurements of the distant universe. I thought that was an amazing result from the Hubble Space Telescope, which I think occurred in the late 1990s. The Hubble Deep Field is a well-known example of, well, we're not sure what we'll see, but why don't we just point the telescope at an empty bit of space and expose for as long as possible, about 1 million seconds or so, and then see what we get. And lo and behold, even though it's a tiny patch of sky, they see something of order 5,000, 6,000, 7,000 galaxies. There are very few stars in there. I think I can only see 2 stars. There's one, a foreground star in our Milky Way, and there's another one. I think that, oh sorry, there was a third one there. That's probably about it. 3 stars and maybe 5,000 or 6,000 galaxies. It's a reminder of just how populated the universe is when we get out to larger and larger distances. And to remind you how small a patch of sky that is, if we put the Hubble Deep Field size next to the Moon, that rectangle there represents the size of the Hubble Deep Field. You can see a tiny fraction. The Moon, remember, is approximately 1/2 of a degree in diameter. So the Hubble Deep Field is only a few arc minutes in size, but it still captures many, many thousands of distant galaxies. The Hubble Ultra Deep Field was a similar picture taken from a different chunk of sky, just to make sure the first picture wasn't a fluke. Yes, when we look billions of years into the past, by looking billions of light years distant, we are of course looking into the past, and we are seeing very remote galaxies, and that tells us something about galaxy formation, because we can look back to the early formation of galaxies rather than the galaxies which are very close to us, which are relatively young compared to the very old galaxies that we're looking at when we go back into the deep field. And as I've already said, if we look at galaxy clusters, we get this effect of lensing, whereby we get this distortion, we get these little arcs, if you like, of distant galaxies. That gives us a lot of information about the mass that's within this galaxy cluster. And when we compare with the mass that we can see, compared to the mass that's needed to produce all of these distortions, we realise that the mass that's present must be a lot larger than the mass we can account for simply from all of the stars and the gas and the dust that we see within these galaxy clusters. This is the main argument behind the reason for invoking the existence of dark matter, is in images such as this, taken by the Hubble Space Telescope and indeed other telescopes, but Hubble was able to resolve some details which were otherwise unavailable up to that time. So a very important role in our understanding of dark energy and dark matter in the early universe. In addition to the scientific legacy, the Hubble Space Telescope has managed to do what arguably all other scientific instruments have failed to do, and that is carry the public along for the ride. Very few people understand, for instance, what the Large Hadron Collider is actually doing in looking for the Higgs boson, but everybody recognises the Hubble Space Telescope, and most people cannot argue that they haven't seen one of the images produced by the Hubble Space Telescope. A lovely quote: "The laws of physics have created these incredible structures, such as the pillars of creation, for instance, and Hubble has revealed them. Through all the research, Hubble has brought the public along for the ride. It has taken the excitement that scientists feel with new discoveries and brought it to non-scientists." That is arguably as important for the legacy of the Hubble Space Telescope as the scientific legacy. So if you've been watching a half hour before I started talking, you've already seen some of the images, but let me just spend a few minutes indulging myself in some of my favourite Hubble Space Telescope images. This is the Helix Nebula, a planetary nebula. It's visible low in the south in the summer months in the constellation of Aquarius. It's quite large. It's quite a fraction of the size of the full moon, but it's not usually bright enough for most people to appreciate that it's a wonderful photographic object, but still one of my favourite planetary nebulas. The Antenna Galaxy, I think this is wonderful because it shows that if you take a couple of galaxies and collide them together, not only do you get a weird and wonderful shape, but you can see that the collision process produces a huge amount of pink, which indicates a star formation region. So when you collide galaxies together, it's not destructive, quite the opposite. It actually produces a burst of star formation because of the tidal effects of the two galaxies interacting with each other. So that's a wonderful image where the colour shows you what's going on, as well as the structure. The Crab Nebula, supernova remnant, perhaps you've seen that too many times for it to be interesting, but the amount of detail that was provided by the Hubble Space Telescope, it's quite a large object, so the Hubble had to take a mosaic to get all of this into its field of view. So superb structure available, and by taking images in different years, it's clear that the Crab Nebula is indeed expanding, as you would expect from the supernova explosion of 1,000 years ago. Mystic Mountain, this is what I used on my splash screen. It's a wonderful image in its entirety, and if you zoom into the detail in the middle there, these pillars, these gas clouds are being sculpted by the very strong stellar winds of stars that are embedded within these structures, and they produce simply amazing looking structures that could be artistic in their own right if they weren't simply natural phenomena. The Sombrero Galaxy, this is something that I tried to image when I was a young astrophotographer, barely a teenager, and I thought it was a wonderful galaxy, and here it's shown in absolute exquisite detail, especially the dust ring around the rim of the Sombrero Galaxy M104. Globular clusters, it's often forgotten that globular clusters have so many stars in them, at least a few 100,000, in some cases possibly 1,000,000 stars in a globular cluster. In many cases, when you try and image one of these objects, especially with smaller telescopes, you find that you can image the stars and resolve the stars well away from the core, but if you try and look into the core of the globular cluster, the stars are so close together they cannot be resolved. The fantastic resolution of the Hubble Space Telescope allowed it to image globular clusters and essentially resolve virtually every star that's in there, because the resolution is sufficiently good, even when the star density is very high, to make out individual stars in the core of the globular cluster. This barred spiral galaxy, I haven't given you its NGC number. I just think it's an amazing structure to have a bar that's basically almost as long as the individual spiral arms. I just thought this was a wonderful galaxy to be imaged. It has indeed been imaged by other telescopes, but I just think this is aesthetically so pleasing. As is this one, the Rose Galaxy, which goes under other names. And again, you can talk about the tidal effects of one galaxy interacting with another, but occasionally you just have to stand back and say, wow, isn't that an amazing image? This is part of the Veil Nebula, which again is so large it occupies a chunk of sky that's much, much bigger than the full moon, and is a popular target with amateur astrophotographers. Here, a very small part of the Veil Nebula has been imaged with various narrowband filters so that the colours that you see here are coming from individual elements. So one colour is coming from hydrogen, another colour is coming from oxygen, another colour is coming from sulfur, and I think there's at least 2 other elements in there. I'm not too sure what they are, but it shows you the power of being able to visualise the structure by breaking it down into the elements that are producing the various colours of light. Pillars of creation, yes, I know it's a bit of a cliche, but it was imaged early on in the career of the Hubble Space Telescope. It was re-imaged for its 25th anniversary. This talk I'm giving now was originally written for its 25th anniversary, even though it's now just past its 30th. But I still think the latest camera being used at the highest resolution to re-image the Pillars of Creation is just one of the iconic views, and again, there are very few people who won't recognise that particular image as being from the Hubble Space Telescope, regardless of being able to explain the science behind what it is we're looking at. It is still an iconic image which has left its imprint on society. And I've already talked about the Hubble Ultra Deep Field, or the Hubble Deep Field, or the Extreme Deep Field. There's been a number of attempts to go as deep as possible, to see as far back in time as possible. The universe is 13.8 billion years old, and the Hubble has already gone back more than 13 billion years. So a very large fraction of the entire age of the universe has been probed by images such as this. So what lies beyond? We've had to think about how the Hubble was put together, how the mirror was fixed. We've had to think about the science that's produced and the getting the public along for the ride in terms of touching the public consciousness. But where do we go from here? What's beyond Hubble? Can't we use ground-based telescopes? Surely we've got the adaptive optics. Can't we get computers to figure out how the atmosphere is moving? For instance, we can shine a laser into the sky to produce an artificial star, and then we can see how that artificial star is moving, and then with the right sort of optics, we can then start moving the optics, physically stretch or stress the optics to try and take into account the movement of the atmosphere to minimize the effect of the turbulence in the atmosphere. So if we can do that and have active optics or adaptive optics, why do we need a space telescope? Well, yes indeed, we can shine a laser into the sky and work out what that atmosphere is doing and correct for it. But what the atmosphere is doing over here is not the same as what the atmosphere is doing over here. It's a turbulent, chaotic system. And so knowing what one part of your field of view is doing doesn't help you figure out what the other part of the field of view is doing. So although we can take a very large mirror like this and say, right, we can collect the light over a 40-meter diameter mirror, the atmosphere is chaotic in the sense that the light hitting one part of the mirror is not behaving the same way as the light hitting a different part of the mirror as far as the turbulence in the Earth's atmosphere is concerned. So even if we do have adaptive optics, we can only achieve really good resolution over a limited field of view, i.e. close to where this particular artificial star is being produced. We can indeed put multiple artificial stars in the sky and try and take all of that into account, but that's not quite the same as a space telescope which has no aberration, or at least no turbulence due to the Earth's atmosphere, and therefore we get the specified resolution over the entire field of view of the chip, whereas if we try and use adaptive optics from ground-based telescopes, we have to try and be very clever to work out how we can take into account the Earth's turbulence. It works fine if we have a very small field of view. For instance, we want to see this exoplanet around this star. If it's a very small field of view, fine, but if we want to take grand vistas over large areas of sky, then adaptive optics is not as good as having a dedicated space telescope. And there are other space telescopes, as I mentioned very early on in this talk. For instance, Kepler had a very specific mission to find Earth-like planets orbiting other stars. And that was done by having a very large, a very large CCD detector. The CCD in the Hubble Space Telescope, for instance, is only a few centimetres or so in size, whereas in Kepler we have this rather large coffee table sized detector, and that was used to stare at one patch of sky. It wasn't surveying stars all over the sky, it was looking at one patch of sky in between Cygnus and Lyra there, and it was simply monitoring the brightness of stars, looking for characteristic dips that would indicate the passage of an exoplanet moving in front of those stars. Gaia is another satellite that has rather ambitious aims. The intention is to measure the positions of something like 1 billion stars within the Milky Way to a phenomenal accuracy, and hence to produce a map of the Milky Way, because if you map where the stars are and you repeatedly do that over and over again, then you see how stars are moving, you get their proper motion, you get their parallax, and you get an idea of how stars are moving within the Milky Way. The intention is to then create a three-dimensional structure map of the Milky Way. The first data release of Gaia has already come out, and already people have made observations such as it looks like there is another satellite galaxy, as well as the Magellanic Clouds, there is another satellite galaxy sitting just on the other side of the nucleus of the core of our own galaxy, which we wouldn't have been able to tell unless we can map out the positions of billions of stars very accurately, and then we can work out what all of these stars are doing. But if we reflect on the Hubble Space Telescope, pun intended there, where we see a reflection of the Hubble Space Telescope, is there a direct successor waiting in the wings? Well, not direct in the sense of another telescope that works primarily in the visible part of the spectrum, but as I'm sure you're aware, the James Webb Space Telescope should be launching before too long. In the graphic I showed you earlier, it said it was due for launch in 2018. Well, that's come and gone, and now we're hoping that it will be launched next year or the year after. The James Webb Telescope will have a much larger primary mirror. You can see the relative scale there between the Hubble mirror on the left-hand side, about 2.4 meters in diameter, and the James Webb primary mirror. Strictly, it doesn't have a diameter because it's a segmented mirror, but it's about 6 meters or so across. It'll be folded up when it's launched, and then it will unfold when it's ready to work. It's not going to be in orbit around the Earth, unlike the Hubble Space Telescope. The James Webb is going to be sent out to this particular so-called Lagrange point, L2. This is a point about 1 million miles away from the Earth, much further than the distance from the Earth to the Moon. And at that particular point, L2, you can park a spacecraft and it will sit there quite happily. Strictly speaking, it'll undergo a little orbit, as indicated by that graphic. So Gaia is currently there at L2. James Webb is going to go and join it. I don't think it'll have to elbow Gaia out of the way. I'm sure they can come to some amicable arrangement as to how they sit close to the L2 point. But L2 takes it away from the Earth, and because the James Webb Space Telescope is going to be working primarily in the infrared, we don't want the warm Earth to bathe the James Webb in infrared radiation. So the James Webb is going to be moved 1 million miles away from the, 1 million miles away from the Earth. So there are other Lagrange points there, but they're not relevant in this context because it has been decided that L2 is where it's going to be parked. What will the James Webb Space Telescope actually do? Well, as I mentioned, it's going to be working in the infrared. So the Hubble Space Telescope has been designed to work in the visible, but it does see a little bit into the infrared and into the ultraviolet as well. So we can get an idea of how it's going to work by just asking the Hubble Space Telescope to take an image in the infrared. So for instance, on the left is the classic image taken in visible light of the pillars of creation, taken with camera 3, the latest camera with the highest resolution. And when used with an infrared filter, we get the image on the right. And you can see that most of the starlight is obscured by the dust in these gas columns here. But if we look on the right in the infrared, we see that we can see through most of that gas and dust, and we can see the stars either embedded in the nebula or beyond the nebula. So by looking in the infrared, we have the ability to cut through some of the otherwise rather obscuring gas and dust that occur in various nebulae. So if we want to understand what's going on inside the pillars of creation, the best way of doing that is to not image in visible light, but to image in infrared. And if we're interested in how planets are forming around stars, which again tend to be very dusty environments, it's very difficult to see inside in visible light, but if you want to see planets forming around stars, infrared is the way to go. Not only that, but if we look into the distant universe, for instance, if we look in the deep field, remember the further back in time we're looking, the further the distance we're looking, the higher the recession velocity of these distant objects. And if they're moving away from us very quickly, that means their light gets redshifted from either the ultraviolet into the visible or from the visible into the infrared. These objects are moving so fast that most of the light they're producing, and a lot of the light that comes from galaxies, is roughly speaking in the visible part of the spectrum. Our sun is a fairly typical sort of star, and it emits most of its light in the visible rather than in the ultraviolet or the infrared. So if that's the same for a lot of other stars that are out there, then if they're receding from us at a very high fraction of the speed of light, or even beyond the speed of light, then the spectrum will be redshifted, and most of that light from the visible will end up in the infrared. So it's anticipated that if we do the equivalent of the Hubble Deep Field but do it in the infrared, then the galaxies are going to be brighter because more light will be in the infrared than we will see in the visible, and perhaps we can push that barrier a little bit further and push our distance limit as to how far back in time we can see. Can we see beyond 13 billion years? Can we see beyond 13.5 billion, 13.6, 13.7? How far back in time can we go towards the Big Bang? If we go into the infrared, then in principle, we can go even deeper into space and further back in time. So I've given you an introduction as to why we need space telescopes and what alternatives we have. There are alternatives, but they will never replace space telescopes. I gave you a little bit of the history, how the mirror was flawed and how the optics were fixed through COSTAR and through correcting the instruments that were then replaced by the shuttle astronauts. And I've told you a little bit about the legacy, touching on a few elements of our scientific understanding being progressed and how it touched the public consciousness and brought the public along for the ride that the scientists were enjoying. And then I had a little brief look at where things might be heading for the future of space telescopes. Thank you for your attention.